We must now think about the important topic of earth grounds and short circuits. Taking the earth as a whole, it can be thought of as a large uncharged body with a potential of 0 volts. Anywhere on land is at 0 volts, and for all intents and purposes, the sea is at 0 volts also. If you connect any electrical equipment to the earth or the sea, it would be said to be grounded, and it will always be at earth potential, that is, at 0 volts. So a ship's hull at sea is grounded. It's at 0 volts. On circuit diagrams, this is how an earth-ground connection is shown. Grounding a circuit is a safety measure. It's like this. Suppose you have some item of electrical equipment in its case. Of course, the leads would be insulated from the case, but the insulation might break down, so that the case would be in contact with the live lead. If now you touched the case, you would get a severe, possibly fatal, shock from the supply. Here it's 500 volts. But if you had taken the precaution of grounding the case, even if the insulation had broken down, the case would stay at ground potential 0 volts, and you wouldn't get a shock. Normally, the ground wire carries no current. It is there merely to provide an easy path for the leakage current if the insulation breaks down. So in the equipment we considered, the leakage current flows into the ground or sea, rather than through anyone touching the live case. But because the earth-ground connection offers a very easy path, a very large current may leak through it, large enough to blow a fuse and cut off the supply. With the fuse blown, there's a break in the circuit, and it is now called an open circuit. So one ground in a circuit may be a safeguard against getting a shock if live metal parts are touched. Two grounds in a circuit are a different matter. A short circuit occurs whenever a component with a potential difference across it is bypassed by the alternative path of low resistance, and it needn't be by two grounds. Such low resistance paths are caused by dampness, insulation breakdown through insulation becoming hard and brittle with age or heat, and by accidental damage. Now let's look at the effect that a ground has in different places in a circuit. Here's a circuit of 3 resistors in series with a 50-volt supply. Let's introduce a ground connection at point A. Can we work out the potential of points A to D with respect to the ground potential of 0 volts? Well, the ground connection doesn't affect the current flowing in the circuit. So Ohm's law tells us that current is V over R. That is 50 over 10, 5 amps. Now point A is grounded, so it is at 0 volts. The voltage across the 5 ohm resistor is given by Ohm's law as I times R, that is 25 volts. So point B is at a potential of 25 volts positive with respect to ground. At point C, the 5 amp current has flowed through a total of 8 ohms of resistance from point A. So the potential at point C is 5 times 8. That is 40 volts positive with respect to ground. And of course at point D, which is connected directly to the positive terminal of the 50 volt supply, the potential is 50 volts positive with respect to ground. In this example, if we had made the ground connection at point D would have been at 0 volts, although connected to the positive side of the supply. The other points would all have been negative with respect to ground, and would in fact have been point C 10 volts negative, point B 25 volts negative, and point A 50 volts negative. Things are a little more complicated if the ground is at some intermediate point. Take this circuit, for example, where point C is connected to ground and will have a potential of 0 volts. The current flowing, V over R, that is 30 over 60, is 1/2 an amp, so the voltage across the 30 ohm resistor is 15 volts. Thus, point D connected to the negative side of the supply is at a potential of 15 volts negative with respect to ground. The voltage across the 20 ohm resistor is half times 20, 10 volts, and is on the positive side of the ground. And finally, at point A, the 1/2 amp current will have flowed from the grounded point through both the 20 ohm and the 10 ohm resistors. So the voltage change across them will be 30 times a half, 15 volts. That means that point A will be a potential of 15 volts positive. Notice that from point A to point D, 15 volts positive to 15 volts negative, the voltage change is 30 volts, the voltage of the battery. There are only 2 or 3 more points to be made about grounds. First, suppose you have 2 grounds in a circuit like this. You remember that this is a short circuit, and the 10 ohm resistor is simply bypassed. As far as your calculations of current and potential go, this is just as if the 10 ohm resistor wasn't there, and the 2 grounds behave as one. Next, you can use grounds as a return path. In symbols, this circuit would be shown like this. Because the resistors are in series, this is called a series ground return circuit. You can also have parallel ground return circuits, which might look like this. And that is all just now about grounds and equipment is a safety measure to avoid shocks. In the next part, we will be thinking about fuses and how they are used to protect electrical circuits.